Welcome ROS developers to this third episode on ROS projects, where we are building a robot that takes the orders in a restaurant to the corresponding tables and then goes back in. So in the previous episodes, we just talked about the setup that you need, the solutions that we decided for, and then in the second episode, we talked about how to create the load sensor in Arduino, how to create a web app that allows the users in the restaurant to to calibrate the load sensor and tell the robot to go to table 1, table 2, or return to base. So in this third episode, what we are going to create is the simulation that allows us to test all the pipeline. So from the web app to the robot moving to the table. And that means the web app communicating with the ROS systems that take in the load sensor data, that have the navigation stack working, that have the feedback that gives the sound when it's calibrated, when it goes, when it comes back, this kind of stuff. And all is controlled by a main program that has a loop and that allows the robot to be working continuously. Okay, so the first step that we have to do to create this simulation is start from an existing simulation. So we will start from an existing simulation of the TurtleBot. So you can download the code from our Git. I'll leave the Git in the video description, but also you can download it from the official repo, or just launch it with ROS Development Studio, which is the most convenient way of doing it. So there we have it. So essentially what we need to do is several things. One, TurtleBot, this design of TurtleBot has the laser on the top, so we'll have to move it to the bottom so we have this space free to place objects on top. Also, we don't need the Ixion, so we won't use that. And then we will try to close this part where all the ports and this kind of stuff, so that it looks a bit more professional, a bit cleaner. So what I did was I downloaded the files and generated with SolidWorks the covers for the new robot. So I've opened the model in Blender. So there we have it. So we have this cover, which essentially is the Kobuki robot with the laser there, and it uses the same system that the TurtleBot uses to bolt and connect the different levels, with some holes here, and then another hole here just for the laser. Okay. And then I place this cover that has some carvings inside, that where you can put drinks essentially. So this is the basic design of the barista robot, of this robot for taking objects to tables in a restaurant. And then the other thing that I created was the 3D model of a space. So you can do whatever you want. I highly recommend you that for the starting point, when you start to do things, do something simple, just because you go faster. This is just block building like this in Blender. So I just added a cube and resized it and give it a material, nothing very fancy. And then what I did was bake the lighting on this. So I won't go into detail how this is done, but essentially you can see that if I remove this light here, it has no effect whatsoever. The only effect that it has here is in the rendering in Blender. So you can see that here the model has some lighting here with lights and so on. If I remove this light, everything goes dark. But the lighting conditions here in what the model of the world is concerned are exactly the same. This lowers the CPU usage and graphical usage, especially in Gazebo, to have very complex worlds. So if you're interested in this topic, please leave it in the comments below and I'll do a tutorial just for that. Okay, so that's basically it. I modeled this world and I use this as basis world to do all the navigation and everything. Once we have the 3D models made, it's time to create our Gazebo simulation and create all the hardware simulated systems, which are basically, the most important one is the load sensor. We need to test that our pipeline of putting an object, then moving around, then retrieving that object, detecting that it has been retrieved, this kind of stuff, we need to simulate it and test it a lot so that in reality it works. I've posted in the video description the Git that has all the code for the rest of the episodes. So we have the barista robot here, and this Git, which is one different from Barista Systems, which is more related to hardware stuff, and the web app. This one is related to the Gazebo simulation and ROS related systems like navigation and so on, that we'll talk in a minute. I've also posted a ROS Development Studio ROSject link that you just have to click it and you'll have everything set up in your ROS development account. So you just have to launch the simulation. You go here and you select, in this case, I created main simple. So here we have the simulation. In this case, the only difference that we have are some aesthetics. And you see this cylinder here, base, which is the load sensor simulation plugin. So let's go step by step. So this is the model that we saw, and let's have a look on how this was done. So let's start from the beginning. So in your Catkin workspace, if you do it in your local computer, I highly recommend you that you install ROS Melodic, just because at the end everything has been designed for Melodic. It works on Kinetic, but it's better to start from the newest version of ROS. So in this case, you're just launching a system that has already Melodic here. So here in Barista, you have to go to Barista Gazebo, and I created this main simple. Launches a world that takes a launch for spawning a robot, and then we are also starting an RViz session. So if we go to our graphical tools, or in your local computer, it will just pop up on your screen. You see that we have our robot here with all the systems basically working as far as the basic systems are concerned. What I created here was a put robot in world. So let's have a look at this put robot in world. And I'm essentially spawning this URDF that it's called Barista Hexagons Astro 16 Pro, but essentially it's just a name. So if we go to Barista, so what I created was a Barista description, independent from the Turtlebot description, and you'll see that it shares some elements and uses some elements from Turtlebot, which are basically the ones that are not modded, so the kabuki and some elements of the posts and so on. So if we go to Barista Hexagons, and I won't go into details, I'll link in the video description a very good course about URDF and robot creation in Gazebo in Robotic Academy. You can have a look and you learn everything that we're using here. It's explained there in much detail. So what we're doing is we are spawning this Barista Kabuki, And then we are putting this barista mods, putting the Hokuyo, and also putting the load sensor. I will talk here just for the modifications that I did, the important ones, to make this work. So in this case, the load sensor. So let's have a look where the load sensor was defined, which is in barista load sensor chakra. So let's have a look. And here essentially is just a link that has some mask to it and so on. The important part is this. So we are using this Gazebo ROS bumper plugin, which is already done. I haven't done it. And this configures everything that has to do with the collisions of this load sensor with everything else. So if we go here, ROS topic list, and we have a look at, we have loads of topics here publishing, but if we go here, this is essentially what this raw plugin is publishing. So any object that collisions with it, it will publish here all the contact points that it has with the other object, and the forces, torques, and so on. But this is too much information. So what I did was I created this filtering system, which is launched here. So this is the simulation, the basic simulation. So the only things that are simulated here are the plugin, which is just the bare bones. So I didn't modify this plugin, and this diagnostic publications. So let's, because it's interesting to know. So if we list here, we see that this diagnostics is published. This is published in the original, the real robot. So I created this diagnostics to simulate some elements of it. In this case, the battery, because we want to publish that information in the web app. So ROS topic, ROS echo. And as you can see, we have the level of the battery here. Published in the format that the real robot uses. So we have the simulation running, and it's publishing some diagnostics based on the real robot, and also some contacts in this simulated sensor. So we have to transform this into the exact same format that the real sensor will give and publish in ROS that we saw in the previous video. And also we will need to transform the diagnostics data into something that the web app can interpret. In this case, we are only interested in the battery life. So we will subscribe to that diagnostics and get that data. So let's have a look. So for that, we are going to launch the following launch file. So if we go to, let me just close this. If we go to launch and we have a look at this SimPic Go return demo, which we will have created at the end of this episode, let's concentrate just in two things. One, this one. This battery charge pub, what it does is subscribe to this diagnostics topics that we just saw there, and gives us a very basic topic of battery status so that the web app can read it easily. This is one thing that we're going to see right now. And the other one is this load sensor start pub, which should ring a bell because we did it last episode. So let's have a look. Let's launch it. So let's launch this SimPic Go return demo, and we're going to go step by step on all the systems. Not all the systems, but the main systems. Okay, let's launch a different shell so that we can have a look at what we are getting here. So, as I said, we are going to concentrate on two launches for the moment. The first one is this simple battery charge, whatever. So if we go to Barista Systems, to the scripts, so Barista Systems, that's here. It's the package that we talked about in the previous episode. Scripts. And we go to battery charge pub. What we are doing is we are subscribing to this diagnostics topic, which is the one that Kabuki publishes, the real Kabuki, and this one publishes a simulated version of it. And then we are publishing this battery charge topic. Yeah. So, and what we are doing is essentially getting, so when we get this callback here, we are getting the battery percentage, which is getting the information and getting in the format that this diagnostic topic publishes, and we publish the battery. So in theory, we should see battery charge topic around here. So let's have a look. Ross topic, echo battery charge. And there you go. So of course this is a simulated version. So this diagnostics publishes something that is, so if we go here in the put robot, this one, this sim diagnostic publishes something that it's totally simulated. So it's just decreasing the percentage of battery during a time, so each second decreases a percentage, but it's to have something that it's exactly as we should have it in the real world. Yeah, so this is the first one. Really easy, right? Okay, and the second one and most important one is if we go to put robot, to this one, we have this load sensor start sub. Yeah. So this load sensor start sub, if we go to systems, if you remember, because we did this in the previous episode, so you see that if the barista was real, we connected to the serial USB and we connected to the Arduino, so on. If it wasn't real, then we launched this simulated load sensor start. And what does this do? So simulated, let's go to Gazebo, simulated load sensor start. And we have this driver, load sensor driver. Okay. So this, what it does is subscribe to this load link contact sensor state plugin and transforms it into load sensor data, which is essentially a float 32, which is exactly the same as the real Arduino. Yeah. How do we do this? I won't go much into detail, but essentially what we're doing is getting the forces and calculating the magnitude, and we're publishing that, and we are just getting that for one contact point. Why? Because this plugin, for some reason, each contact point has the same force, so it multiplies artificially the forces that interact with the object. So essentially getting one, then we have the data. So let's test it. So now that we have the sensor working, let's test how it works. So for that, we're going to use another launch that I created, which is spawn delete server, which is spawn launched just here. And this is only when it's simulated, because in the real robot, we will just put the object and that's it. So this delete server essentially launches a server that interfaces with the Gazebo spawning elements. This is based on a code made by Florian Weishart, and I adapted it so that it was easier to work with, or at least for my intended purposes. So we go here and we call this service, which is the one that we are starting. So ROS service call bam. ROS call. Then let's see that it auto-completes, correct. And now we have to place here models. We have to place here the position. In the robot namespace, it's the action, so spawn. Model, spawn. Package. And the name of the model, which is standard Apple. Yep. Why I'm using this kind of messages which don't correspond exactly to what we are doing is just because I recycled this already done service message to go faster, really. Okay, so hit enter, and there you go. So we have our nice apple here. So if we have a look at ROS topic echo, our beloved load sensor, we are now getting around 200 grams. And if we check the weight of this apple, in this case, it's around 200 grams. So perfect. But not only that, but remember that this published other stuff. So if we do ROS topic echo and load sensor info, there we have it. So we have the object that says that we have to calibrate it. So let's calibrate it. It was load sensor, and then we had to write here true. Oops. There we go. So now we have the object loaded. And if we go to the simulation, let's go to the simulation, and let me put this like that so we can see both things. If I go to the simulation and I get rid of the apple, let's say I move it out of the way, object was removed. Fantastic. So now that we have the hardware working, so we have our load sensor, we have the diagnostics that simulate some of the systems that Kabuki has, and we have our robot already done here with the laser on place and all that stuff. It's time to do navigation. So to do that, if we go to, let's close this. If we go to this main launch that we have here, we are launching this localization demo. Okay. And this essentially, this and this ROS waypoint generator are the two main elements that we use to generate the map and save the waypoints. Okay, so how does this work? Let's have a look. So if we go here, we see that when we launch it, the RViz got all the cost maps, the map already done, and this kind of stuff. So let's do an example on how to create a new map and how to save the waypoints. Yeah. So let's get started. So for that, we remove this. Now we don't have any mapping whatsoever. It's just having the old information. So let's relaunch the simulation again, just to be on the safe side. Okay. So while it's loading, we now let's close the let's leave the shells for now. And I'm going to launch the mapping launch. So these, you can find all of these inside this Costa robot launch. So we have a G-mapping demo, a localization demo, and a safe map. So let's do a navigation example. So here I got some instructions. So the first thing is creating the map. So, well, the first thing is having the simulation working. So first thing, we have our simulation working. Then we launch our G-mapping demo. There you go. So registering the first scan. So we have our map there and our lasers. Okay. So let's put this around here so we can see it a bit better. Not much better, but there we go. There you go. Okay. Now the second step is, okay, we have to launch our, when we want to save the map generated, then we have to execute this command. So we launch the keyboard teleop for the simulated version because in the real one, there are some differences due to time. In theory, it should be exactly the same. So now we move around and we generate our fantastic map. So as you can see, it's a very tedious process. You just have to move around in your environment and map it, everything, okay? Okay, great. Then let's say I want to save this fantastic map, which I would say it's really bad. But here, we just click here and the map should have been saved. Where in this case, if we go to Barista, Costa Robots, and then generate it, you should see here new map, which if we download this fantastic image, you can see that is the map that I generated, which is rubbish because you have to spend here time going to each nook and cranny of the map to have it perfectly mapped, okay? Okay, once we have it, then we go to the next step, which is generating the waypoints. So here we have ROS launch barista, blah, 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 new map, and we do the waypoints. So we launch this instead of the G mapping. So let's launch this. Okay, so now we have this absolutely rubbish world. So we now create some waypoints. So for example, we put a waypoint here, which we will call base. So there we go. So this was saying, hey, I don't have any waypoints. So there you go, you have a waypoint. And now we have to save that waypoint. So for that, we have this server, which is called Waypoint Save Server. So if we do a ROS service call, Waypoints Save Server, you see that we can give it a name. So let's have a look. No, sorry. Let's put it a bit smaller. This is also a bit smaller. Let's check that we have the waypoints. Yeah, we should have it. Okay. So now I give it, let's say, home. Home. Okay, so now we have a waypoint assigned to that location that we will call home. Let's move the robot around, okay? Let's we could move it with navigation if the map was correctly done, but as you can see, it's not located properly or anything. So let's have a look at the real robot. There we go. So for example, we want to generate a waypoint here. Yeah, so let's move the robot there, more or less, to have a reference of where we are. Okay, and now we just put a point around there, and then we save it with table 1. There we go. So now we should have that name there assigned to that position. Yeah, more or less. Okay. Bear in mind that it's not positioned, so he doesn't really know where he is now. But hey, at least it's putting the waypoints where it should, okay? So having a map that it's correctly positioned, then we would see here exactly what we should. Yeah? And that's it. So now we have the waypoints and so on. So this program that we launched here, when we exit, it will save closing and saving waypoints system. So this is saved in a pickle file, which let me have a look where we have it. I think we have it here. Waypoint saved, and yeah, so new map pickle. So it's saving the waypoints in pickle format. This is much easier to retrieve data afterwards with Python. And that's it. So now you know how to generate a map, to start the localization, and to generate the waypoints. As far as the configuration of the navigation is concerned, I'll give you just 5 cents of it. So we have basically this Costa robot package, and inside it we have some parameters for the navigation. So one of the most important ones is the planner, which it's giving the max velocity and the minimum velocity that we intend to give it. So maximum and minimum velocity. So if you give it too much, the navigation will go really fast, but then it might not resolve some situations. So it's better to be conservative, especially in the real robot. That's one. Then another one is, another important element is when you go to AMCL, the name of the topic. So if you have a different robot, the topic may be different, and also the base footprint, it may be different. So you'll have to change these parameters here. So bear that in mind also. And also in the move base, you have to take into account the topic that it uses to move the robot. So this should be the command vel that when you publish there, you move the robot. So you have to give it to the move base so that it works and the navigation can move the robot. Okay, and the final part of this third episode, where we created the simulation, we have navigation working, we have the load sensor working, we have the world, the simulation with the model, everything. So now the only thing that remains is the sound.